this technique called dynamic light scattering. It's a very simple to use technique. The instrumentation is quite simple to use, even though the physics behind it is very complex. And the dynamic light scattering instruments are in all the big biopharma companies and many of the SMEs, because it's relatively inexpensive compared to crystallography, NMR, centrifuges, all this sort of stuff. It's quite compact, and it doesn't take too much training to operate, because all the physics is done for you, all the computer programs, and the information content you get is very high. So very popular in biopharma, which is why you need to know what this technology does. Did you sneak in? Did you come in with that group?
What?
Yeah, I didn't see you come in.
I said hi.
Right. Okay. And apologies if the message didn't get through. You didn't miss much. All we were just talking about was the Corona crisis, really, and what was going to happen. So thanks for seeing this out. It's quite sad in a way. Anyway. Okay, so DLS, you just put your solution in these little pipettes, like you get with spectrophotometers. There are variants of that. You've got flow cells and things with some of them. And like with the conventional light scattering we talked about in BIOS4005 molecule, you have a solution of your molecules, or whatever, your biomolecular assemblies. So you could look at coronavirus with this, because that's quite the right size to study with this type of technique. You shine laser light at the solution, and then you measure the intensity of the light scattered at an angle. But instead of the light scattering we showed you before, the classical light scattering, where we looked at the average intensity as a function of angle to get the molecular weight and the gyration radius and things like this. With this technique, it's a bit different, because what we're looking at is the movements of the molecules, because the molecules are moving about through Brownian motion. The rate at which they move about depends on their sizes and shapes. So what we're doing is, because they're moving about, the intensity of light scattered will fluctuate. How fast that fluctuates depends on how fast the particles are moving. And the smaller the particles, the faster they move. The more compact the particles, the faster they move. Okay? So it's a bit like sedimentation in a way. The sedimentation, the rate at which particles sediment, in this case, the bigger the particles, the faster they sediment. But like dynamic light scattering, like the more compact the particles, the faster they sediment. So dynamic light scattering is, in a way, like the ultracentrifuge in terms of looking at the sizes and shapes of the molecules. I need a detector which can pick up these fluctuations in intensity. In terms of reading, there's this book, it's old now, this is 30 years old, Laser Light Scattering in Biochemistry, and it's based on a meeting that I organised many years ago with Dave Sattel, who's an expert on light scattering applied to microorganisms, and Vic Bluefield, who used to be president of the American Biophysical Society, expert on light scattering, and now long since retired. That was a fabulous meeting. It really was. So this book you can access. I don't think I put it online, but it's maybe I should put it online because you can't get to libraries now, can you? Okay. Do you want me to put it online for you? Yes. But this is online as well. Again, with the restriction, you don't maybe add to your friends who are not doing the course. This is specifically for use on the course. There's a chapter in there. So I'll get laser light scattering and biochemistry online for you guys. Okay, so just a bit of theory. You don't have to reproduce all of this. All you need to know is the basics of how the technique works and what it can do, what it can measure, and what are the limitations. Because if you get jobs in biopharma or you go on to academia and things, and you need to make a decision which technique is most applicable for the particular problems that you want to solve. So you need to know what the techniques can do and what are the limitations. The same as with MRes CD spectroscopy, which we'll talk about in the lecture after me. So dynamic light scattering is a way of getting something called the diffusion coefficient, how fast molecules diffuse, which depends on the structure and size of a molecule. And measurement of diffusion coefficients with dynamic light scattering, we can get information quite quickly on the distribution of sizes of particles, particularly for larger particles, which the ultracentrifuge is very large particles the ultracentrifuge can't cope with. So this is very good for looking at distributions, particularly involving biomolecular assemblies, including things like the coronavirus. Yeah. But obviously, if anyone's going to use this technique for researching these dangerous bugs, then there's all sorts of restrictions and requirements in terms of the, get all hooded up and all this sort of stuff. But you could use this technique of diffusion measurement with dynamic light scattering, looking at corona. In fact, we use it a lot for looking at the destruction of bacteria, and following how bacteria change when they germinate, bacterial spores when they germinate, and what happens when you apply disinfectants and things. It's a great technique for looking at large macromolecular assemblies and size distributions, and also changes. You can follow a process as a virus particle, for example, changes when some viruses, you add calcium and it'll take up water for some reason. You can follow changes in size. You can follow bacteria as they grow or as they are destroyed. You can follow the self-assembly of macromolecules, but on a time course of seconds, minutes, hours, not microseconds or picoseconds. It can't cope with that, but seconds, minutes, hours, days. And it's also used for looking at crystallization of proteins. In the lecture you had was it Jan gave a lecture or Dave Scott on crystallization of proteins? Dave. I'm sure Dave would have mentioned the fact that it's not easy getting proteins to crystallize. And some very interesting ones just won't crystallize. They're called stubborn non-crystallizers. And dynamic light scattering, there's a way of seeing if these methods can cause nucleation and growth of crystals. So the DLS instrument dynamic light instrument is very, very useful. So what we're going to do is just go through the diffusion coefficient, techniques for attaining it, and discover some experimental points. It's not the only technique, DLS. When I say DLS, I mean dynamic light scattering for measuring diffusion coefficients, but it's the most important one. And then the uses. Okay, so this is a bit of theory. You don't have to reproduce this. This is just to show you where it comes from. So diffusion is a manifestation of the ability of a particle to move under the influence of a concentration gradient or under the influence of Brownian motion, thermal energy. And it's all linked in with the laws of thermodynamics, the fact that if you've got a concentrated solution here and it's dilute here, that is not favourable because nature likes everything to be evenly distributed, maximising the entropy. So there'll be a driving force for molecules to move from a region of high concentration down to a region of low concentration. We call this movement down a concentration gradient, and this looks complicated here, but this J is simply represents the flow of macromolecules or molecules down a concentration gradient. So dc dx is how concentration changes with distance, and d is the constant of proportionality, which we call the diffusion coefficient. There's a minus because the direction is down the concentration gradient, so it's from a region of high concentration down to a region of low concentration. And when all the concentration is the same, diffusion will stop. That's right. So that's the diffusion coefficient. And it also appears with Brownian motion, where you get this displacement because of thermal energy. So x squared with the bar across is the average square displacement of a particle. So the square gets rid of all the negative distances, so negatives, positives are all removed by the square. So it's the mean or average square displacement of a particle equals twice the diffusion coefficient times time. So to get d, if you can measure that and divide by 2t, you get the diffusion coefficient, which is the same diffusion coefficient as in this equation here. So if you measure the diffusion coefficient of hemoglobin by concentration gradient work, or you measure the diffusion coefficient by Brownian motion, which is what we use with dynamic light scattering, you'll get the same answer, assuming the techniques are working correctly, of course. So, and it's this which is most relevant to dynamic light scattering, because we're looking at the motions, the movements of particles, thermal energy. That's right, I think that's okay so far, not too difficult. Right, we'll soon change that. Now the diffusion coefficient which we measure will depend on the solvent in which your molecule is in. So it's in a thick, viscous liquid. Obviously it will move slower compared to just water. So what we do is we make our diffusion coefficient measurement with whatever solvent we are working in, and then we standardize, normalize to standard solvent conditions, like we did with the sedimentation coefficient, remember? So it's the standard conditions for comparison is the viscosity temperature of water at 20 degrees centigrade. So we do this correction, you make your measurement in your buffer or solvent at a particular temperature, and then you correct it with this formula here, 293.1, that's the absolute temperature of 20 degrees centigrade, divided by the absolute temperature of your measurement, times the viscosity of your solvent at the temperature you measured it at in the DLS instrument, divided by the viscosity of water, 20 degrees centigrade. And you're all experts on viscosity now, we've done all that. Yeah. Oh gosh, the practical, yeah. That's easy. See how this comes in logically after you've done the viscosity. Yeah, so good structure, of course. Yes. I'm filling in the module feedback for you. You shouldn't do that. Right. And then you've got this non-ideality again. Non-ideality always comes in. So we've got to correct for non-ideality. So we make measurements at a series of concentrations and extrapolate back to zero concentration. Now, luckily, with the diffusion coefficient, you've got opposing types of non-ideality coming in. You've got thermodynamic non-ideality caused by the size, exclusion volume, and charge effect repulsions. Then you've got a different type of non-ideality which comes from particle moving and there's backflow, and also particles may be interacting and may be associated, and that causes a different slope. So you've got a positive or negative slopes depending on the strength of these opposing forces. So these can cancel out. So the result of this is that non-ideality is not as serious with dynamic light scattering as it is with other techniques like viscosity, sedimentation, standard light scattering of molecular weight measurement. So this is a good thing. So with some luck, non-ideality is not serious with dynamic light scattering, unless you go to very high concentrations, which is what you need when you're looking at antibody formulations at very high concentration. There's a lot of interest now with the theoreticians as to what happens at very high concentration antibody solutions, and when you look at it with dynamic light scattering. So, but conventionally you extrapolate back to zero concentration, but it's not as critical with dynamic light scattering. That's one advantage of the technique. Right techniques, this is just, you can get diffusion coefficients with centrifugation and also with NMR. Did Dave Scott mention measurements of diffusion coefficients with NMR? No, we can. And just a revision to types of light scattering, turbidity, that's just measurement of the zero angle. When light passes through a solution, it will get absorbed, and so the intensity of light will be different coming out because of absorbance. But even if you are away from absorbance maximum like 280 nanometers and things, if your solution is concentrated, the intensity will drop because of loss of light through scattering. And turbidity is a measurement of the loss of light at zero angle, the intensity at zero angle caused by scattering. So it's a scattering experiment, but slightly different from measuring the scattered intensity at different angles. You're measuring the loss of intensity at the zero angle. There's light scattering, classical, we've done that before, that was in BIOS4003, and now this light scattering. Right, so this is the technique. Again, you don't have to reproduce this. This is how the light scattering technique works. So you've got your monochromatic laser radiation, which is conventionally red light, helium neon laser, but you can use argon lasers, which are green or blue, helium cadmium lasers. So you've got your solution of biomolecules, and then you measure the light scattered at an angle theta, picked up by a detector and passed to a computer for processing. And what you're measuring, because the particles are moving about, basically the radiation at a fixed wavelength is coming in and is absorbed by the molecule and re-emitted at the same wavelength. Okay, that's what scattering is about. No absorbance, it's the same wavelength is scattered. But because the particle is moving, when it emits the radiation, the detector is picking up something that's emitting radiation at a particular wavelength that's moving relative to the detector, and this is called the Doppler effect. And it's the same as when you hear an ambulance or police car coming at speed and you're stationary and you hear dee doo dee doo dee doo dee doo dee doo dee doo dee doo. The frequency of the sound wave will change because the ambulance emitting the noise is moving relative to you. So for the ambulance driver, it sounds the same. But for you, listening to the ambulance as it's moving, or police car, or whatever, the frequency will change. And this is what the detector picks up, this frequency change. And because the particles have a distribution of velocity, not all moving at the same velocity, that some are moving faster than others, then they will emit waves, or that's picked up by the detector, which are quite close in terms of the apparent wavelengths. And when you get that, when you get waves which are close together in terms of the wavelengths, you get this this beating where not only does the wavelength change, but the intensity changes. It's when in the old days, now it's all digital radio, but in the old days, when you were tuning into Radio Moscow, not that you do that, but tuning into some Radio Bucharest or something on these big shortwave or medium wave radios, and then you find there's lots of other radio stations nearby, you know, Radio Mexico or something and things, and then what happens is that the two interfere because the wavelengths are very close to each other, and you get this upping and downing of the amplitude of the volume, and this is the Doppler effect. So that's why the intensity changes caused by the molecules moving about. It's related to something called the Doppler effect. From your point of view, you can just think, well, the molecules are moving about, therefore the intensity changes. Is that satisfactory? But the real explanation is in terms of this Doppler effect caused by the absorption and emission of waves, and the fact that they're all moving about and the detector is stationary, and you get this change in frequency. Different frequencies all very close together, which cause this intensity fluctuation. And how fast this fluctuates depends on the size of the particle. So the instrument, what it does, the dynamic light scattering instrument, it compares the intensities at different times, and it compares how these intensities change with time. So when it compares, we have this word called correlate, which is just a fancy word form of compare. So we correlate the intensities at different time intervals, and in the old days we used to have to set this comparison time, ourselves, and that would depend on whether we're looking at big particles like bacteria or small particles like proteins and things. The user would have to set the comparison time interval himself, herself. Now that's all done automatically by the computer software on the dynamic light scattering instrument. Okay, so you have to do nothing. Just press a button. So it's scientifically frustrating not interacting with the instrument, but then it's very easy to use. And you compare 64, 128 or 256 time intervals depending on how expensive your dynamic light scattering instrument is. 64 cheap, 128 moderate, 256 expensive. So we've got the 128. This is no, because you don't need to compare 256. That's maybe your GSKs, people like that has that sort of stuff, but we don't need that. So these are the comparison times, sample times, which you set, and at 64, 128 or 256 intervals. All right. Do these comparisons and you average over a period of time, and then what you do is work out this. It's called a normalized correlation function, G. So don't worry about all this. This is just the formula which shows you you're comparing intensities at different times and then performing some sort of average to give you a measurable set of data. And what you do is you plot this, where are we? The log of this correlation parameter, -1, against this channel number. And when we did this experiment years ago, you can see that we had 64 channels, so we had the cheaper range instrument then, but it was absolutely fine. And what you do, you plot this correlation function as a function of time, and that means as you go, see, if I compare that intensity with that intensity, then at small time intervals the correlation intensity is high. But as I go further away in time, the correlation gets weaker. So it's how fast that correlation changes gives you the diffusion coefficient. And that's what this plot is here. It's plotting the log of this correlation function against time. And so how fast this correlation drops with time depends on the diffusion coefficient. So the greater this change in time, the greater this drop in correlation, the greater the diffusion coefficient and the faster the molecules are moving. And that's what the device measures. It compares the intensities at different time intervals, seeing how they correlate, how they compare, and if things are moving fast, then the correlation will drop quickly with time. And then the maths shows that if you plot the log of this correlation parameter, -1, against time, in this case these channel numbers, time intervals, then the steeper the slope, the greater the diffusion coefficient. So for this big molecule called dynein, which comes from, it's a motility protein, whose molecular weight is 2.5 million, that has a diffusion coefficient corrected to standard conditions of 1.1 times 10 to the -7 centimeter squares per second. So it looks small, but it doesn't. You'll see how important this is when we use this later. That's how you measure the diffusion coefficient. And it's all done by the computer. Jane. Yeah, so you just put your sample in, you press a few buttons, it does works out what sample time to use, and then away you go. And then you average and average and average and average, and then it comes out with a set of diffusion coefficients measured at different time intervals. Okay, just one word of warning that if you've got an asymmetric scatterer, then you need to extrapolate back to zero angle, because there's a complication caused by not just translational diffusion, but this is called rotational diffusion, tumbling motion. So what you actually measure is an apparent diffusion coefficient, which is affected by tumbling asymmetry. But if you've got a spherical particle, then these tumbling effects are negligible.
What is it? Asymmetric scattering?
Something which is elongated molecule. Okay? So myosin or a rod-shaped polysaccharide, you have to be a bit careful with how you interpret the data.
So it's not the device is slightly tilted,
No. No. Right, let's zip through this then. So yeah, we've done that. We've corrected standard conditions, and if necessary, extrapolate to zero concentration. This is what an instrument used to look like. This was back in what's now the Barn building, used to be where our old NCMH laboratories were. And this is a scientific instrument, okay? There's the laser. Your solution goes in a cuvette thing. Where are we? What's the cuvette? What's the cuvette? What's that called? Here it is. Your cuvette goes in here. This is a baked bean tin, by the way. It's expensive. This one came out a lid, so we got a baked bean tin and painted it black. It goes in here in a water bath, controlled temperature, and then you position the detector angle. In this case, it's 90 degrees. And then it goes to a what's called a computer correlator. The correlator correlates the intensities at different times, and then the signal goes to the computer. And you can see how old the computer is. That was taken not long after I came here in 1986, I think we got the old DLS. Then that's what it looks like today. So everything is now compacted. The laser is small diode laser. It's linked to a computer, of course, but all the correlation and things happens in here in the computer. So it looks like a compact little box now. And this is the cuvette. There's your solution. And also, we can do what's called electrophoretic diffusion. We can apply an electric field across the solution as well. That's a different story. We're not going to cover that now. So that's what an instrument looks like now, and that's what it used to look like. A bit frustrating, isn't it? That's a box. That's how it goes now. This is health and safety, the lasers enclosed, everything else. And, they would discourage this type of setup now. But, scientifically, I don't think it's good. And then your solutions have to be very clean, because dust scatters very strongly. So this is what we used to do. We used to have these special devices for making sure that the solutions inside here were absolutely clean. So first we have to make sure the cuvette is clean, no dust, so that there's dust in the air and everything else. So this was the device designed to, when you wash the cuvette out and dry it, the dust particles don't get back in. But nowadays, the computer software is very good at extracting out contributions from large particles. Yes, okay. Sorry, Lindsay, sorry.
How do you set the angle in the new machine?
Right, well, in the old instruments, here, you just twist the goniometer and you can look at a range of angles. 90 degrees is a popular angle, basically. You get a nice strong signal. And unless you're dealing with asymmetric scatterers, large polysaccharides, 90 degrees is fine. If not, you do measure a series of angles and extrapolate back to 0 angle to get rid of the rotational diffusion contribution. But most modern instrumentation now, you can't do that. This has got just 2 angles. One high angle and one low angle. So if you're worried that you're getting rotational diffusion effects, you can check by looking at both angles. But usually the low angle measurement, which is 12 degrees, is sufficient to remove asymmetric scattering effects. But you've got that check that that problem is there because you just specified the angle 173 or 12 degrees and it will make the measurements for you. If not, this is sort of instrument which is typically in industry now. So if you wanted to do the multi-angle measurements, you'd have to go to a specialist laboratory to have that done. But that's very rare now. Okay, so good point. High change angle these days. It's and the point here was that you try and make sure your solutions are clean, but there's no need to go to this extent now because the computer software will eliminate the contributions of dust. Right. So let's just quickly go through this and what we can do with the diffusion coefficient once you measure it. And these are all relevant to biopharma. What's the molecular weight, size, conformation, polydispersity, particularly with this technique, and the dynamics of processes, looking at crystallization and this sort of stuff. Okay? Let's just quickly have a break. Molecular weight. This is called the Svedberg equation. That's the sedimentation coefficient. That's the diffusion coefficient. That's the specific volume. You know all these are all friends. So we get the molecular weight if you know the diffusion coefficient and the sedimentation coefficient. And where that comes from is that these are the equations linking the diffusion coefficient with the frictional ratio, which is a measure of the resistance to flow, and the sedimentation coefficient with the frictional coefficient. And we did that in semester 1 in the BIOS4008 module. So the Svedberg equation just combines those 2 equations together to eliminate the frictional coefficient. Okay?
So what's then the difference between frictional coefficient and viscosity? Since viscosity is also...
Yeah, viscosity is a resistance to flow of the whole liquid. Okay? The bulk liquid. So it's volume molecule and how it affects the whole liquid. The friction coefficient is the movement of the molecule through the liquid under the influence of a gravitational force. So you're pushing the molecule through the liquid. That's the difference between friction and viscosity. Is that clear? Yeah, good question though. So by combining these 2 equations, you eliminate the friction coefficient of molecular weight. So that's 1. 2. Size. Yeah. Stokes. Yeah, Stokes is one of these Victorian scientists with beards. Remember we showed you James Clerk, Maxwell, Lord Rayleigh, and so Stokes is another one of these guys with the beard. I think it's only Michael Faraday actually that doesn't have the beard. But so Stokes is one of these guys. He came with this equation, linking the radius of the particle. It's called equivalent radius because the way your particle may not be quite spherical. It might be ellipsoidal or something else. it's the equivalent radius of the sphere. So it's the equivalent sphere and the radius of that sphere. So, and we're always making approximations, so you know, what's the approximate size of the particle. This is very useful, and this is how it's related to the diffusion coefficient. The bigger the particle, the smaller the diffusion coefficient. Or the bigger the diffusion coefficient, the smaller the particle, because small particles move faster than big particles. This is related to the gas constant. It's just the gas constant divided by Avogadro's number, is that right? Kb equals R over Na, you can check that. And that's the viscosity of water, 20 degrees centigrade. So we get the size, molecular weight, size. Here's some sizes. Lysozyme, hemoglobin. There must be a misprint here. Why is there a misprint? What? No, that's right. Okay, and albumin, of course, is my favourite molecule. But the method of sizing works particularly well for larger particles, including viruses such as this plant virus, turnip yellow mosaic virus, and it would of course work for coronavirus, but I think the facilities for doing those measurements would be very different from what we have, for example, in the NCMH, but it is possible to use this sort of instrumentation to look at the sizes of these types of dangerous viruses, but under special situations, and also much larger macromolecular assemblies such as bacterial spores and other types of microorganism. So the method is well suited for that. And we ourselves at the NCMH have done several research projects involving plant viruses and bacterial spores, indeed bacteriophages as well. Right, the third application is in terms of conformation. Now we just clarified the difference between viscosity of solutions, which refer to the resistance to flow of the bulk solution, that is the macromolecules dissolved in the solution, whereas friction refers to the movement of macromolecules through a solution under the influence of a gravitational, or it could be an electrical field. So viscosity and friction are different. Another misconception that students often have is the difference between density and concentration, because they both have the same units of grams per mil, grams per centimetre cubed, or kilograms metre cubed in SI units. Density refers to the properties of, again, of the bulk solution. That means the mass of the whole solution, that is macromolecule, plus the solvent, the water or whatever, and solute particles per unit volume. Whereas the concentration refers to the mass of the molecule or macromolecule dissolved per unit volume of solution. So density and concentration are not the same, they refer to different properties. Right, so conformation by dynamic light scattering. So this involves the measurement of this shape parameter here, P, which is the Perrin shape function, Perrin, another prize winner like Svedberg. And we mentioned this in the antibody biotechnology module, where we were modeling the conformations of antibodies using bead models. And we can get this from either the sedimentation coefficient or the diffusion coefficient. And for that we need to, first of all, transform these values with the assistance of molecular weight and one or two other parameters to give this ratio called the frictional ratio, which is the ratio of the frictional coefficient of the macromolecule or macromolecular assembly to the friction coefficient of a spherical particle of the same mass and volume, same mass and dry volume as your particle. So this value will be 1 if it's a dry sphere. It'll be greater than 1 if the particle is asymmetric, or if the particle is hydrated due to the interaction of solvent, water or buffer or whatever with the macro molecule. And then, having corrected for the swelling due to hydration or water association, we end up with this parameter, which is a function only of conformation, the Perrin function. So I've just said all that, and these are the formula which help us get the frictional ratio from either the diffusion coefficient here, don't forget after correction to standard conditions, or the sedimentation coefficient. For example, from the diffusion coefficient, we can get the frictional ratio from the diffusion coefficient and the molar mass, and these are the parameters here, Boltzmann constant, that was the viscosity of the solvent here, absolute temperature, specific volume, or from the sedimentation coefficient, again from knowledge of the molecular weight, this partial specific volume, and of course the sedimentation coefficient itself. So either way will give us the frictional ratio. This is much quicker to measure, but we tend to get a more accurate value if we use the sedimentation coefficient, if you have access to this type of equipment. Then we correct the frictional ratio for the hydration or swelling of the molecule due to water association. This is the Vs over V bar. The reciprocal of this is what we call the swelling ratio. You need to refer back to the viscosity practical for that. Typically Vs has a value of 1 for proteins, and higher than this if there's sugar involved, or you can work in terms of the hydration, because Vs equals V bar plus delta over rho naught, density of the solvent, where the hydration value is the average value for a protein molecule is 0.35 grams of solvent bound per gram of protein. And don't forget, this is a dynamic association, so the water is not permanently bound to a protein or macromolecular assembly, but is in some sort of dynamic equilibrium with the surrounding solvent. So, to making these modifications, adjustments to the frictional ratio, we can get the Perrin function, which is a function of shape. This is how the Perrin function changes with axial ratio for prolate and oblate ellipsoids. So it's a complementary function to the viscosity increment, which you met with the viscosity practical. And for ellipsoidal work, these parameters are built into the program called ellipse1, which are used in the viscosity practical. You just select the parameter you want to use, so you can get the simple axial ratio of a macromolecular assembly using the parent function or the viscosity increment in the program ellipse1. There are other shape functions as well, but these are the two principal ones we meet in the MSc course. So the value for a sphere is 1. It would be greater than that for more extended shapes. For molecules like antibodies, we can't use simple ellipsoidal representations. We can for the domains, the Fab and the FC domains, but not for the intact antibody molecules. So for these types of asymmetric shapes, we can use Hydro, Solpro, these types of programs which allow us to do B modeling, such as this IgE, or this slightly modified B approach called the B shell modeling approach, it's IgG1. So when we gave that lecture in BIOS4004, when we came up with these, when there's p-values, we're trying to match the experimental value with the model value to find the best model. This is, you know now, where the p function comes from. And then you've got to be aware of this uniqueness problem, the fact that you get a model which agrees with the experimental data, but to take into account that there may be other models which also agree with the data, you use different types of functions from, for example, X-ray scattering and the RG parameter and things. Just to reiterate, the dynamic light scattering with the diffusion coefficient can give us the p-value, but you can also get the p-value from the sedimentation coefficient as well. This method is quicker. This method is generally more accurate. Right. Perhaps one of the most important applications of DLS is in terms of evaluation of the distribution of sizes. And this is a particularly good example of that and relates to the CD lecture of Dr. Phillips Jones, which follows this lecture. So vancomycin is an important antibiotic. It's a very small molecule. Its molecular weight is 1500. So when we use DLS, it comes out as a very small molecule. This is the peak for vancomycin. So it's a very small molecule, very high diffusion coefficient, and low value for the hydrodynamic diameter. And don't forget, the hydrodynamic diameter is simply twice times the Stokes radius or the hydrodynamic radius. And in running the software in these DLS instruments, you have a choice of working in diffusion coefficients, in the hydrodynamic radius, or the radius of the equivalent sphere, or the hydrodynamic diameter, or the diameter of the equivalent sphere. Here it's set for diameter. And then we're looking at the interactions with mucin. Mucin molecules, as we find later on in this module, is the molecule which was part of mucin is not part of mucus. Mucin is a very large glycoprotein molecule, usually several million molecular weight. And actually this work came from a project involving Haley Coop, who was an ABT project student, and we at the time we had some students in the NCMH working on mucins, and somebody else working on vancomycin. So we wondered what we could get Hayley to do, and I had this idea, let's just look at how vancomycin behaves in the presence of mucin, because vancomycin is applied intravenously. It's also applied orally, depending on the type of infection that was being tackled. And there was this curiosity as to what this molecule did in the presence of mucus. And vancomycin is quite an interesting molecule. It's got these sugar residues here on this peptide backbone. So how would it get on with a mucin molecule, which is large molecule, protein backbone, and loads of sugar chains coming off, so 80% of the sugar of the molecule is sugar. So how would these two molecules interact? So, and we looked at intestinal mucin, and this PIM doesn't stand for PIMS, a type of drink, but PIM stands for pig intestinal mucin. We couldn't work on human intestinal mucin for health and safety reasons and things, but we could work on pig intestinal mucin. And the black here is the signal for the mucin. So it's got actually two peaks, one here and one much larger one here. This is a very large molecule. And what happens when we mix the mucin with the vancomycin at different ratios? Do these molecules interact? If they didn't interact, then we'd still see these peaks in the same places when we mix them together, but in the mixtures we don't see that at all. You see these higher molecular weight, higher size peaks, so this clearly shows there's an interaction. And this is borne out also by the ultracentrifuge and also in what's called environmental scanning electron microscopy. And if you're interested, then there's this paper. This is Mary Phillips Jones, who's going to be giving the CD lecture, and a mixture of experts on mucins, and Nikki Weston and Chris Parmenter are experts in the environmental scanning electron microscopy facility which we have at Nottingham. I'll put this paper up on the Moodle. It's open access, so you can read this and see how your predecessor, Hayley, working with Ryan Lithgow. Ryan was an MRes student, and this is Vlad, who many of you know. Vlad Dinu, who did the ABT course and then went on to do a PhD with us. He's now an EPSRC research fellow in the NCMH laboratory. That's an interesting application, showing you how easy it is to get these distributions. And all that stuff I showed you before about sample times and things, that's all taken care of by the software within the instrument. And then finally, looking at dynamics of processes. By dynamics we mean processes that occur in the order of seconds, minutes, hours, time scale. We can't look at microsecond, nanosecond changes. It's really for seconds, minutes, hours. And for example, if we're looking at the microorganisms with viruses, looking at the interactions of microbes in the environment. For example, viruses, certain plant viruses uptake water in response to calcium ions, and this one, southern bean mosaic virus, is another attractive name. You just had turnip yellow mosaic virus. There's the tomato bushy stub virus we met before earlier in the course, and this is the southern bean mosaic virus. You can see what happens. This is the measurement of the diameter again, and this is the point at time zero where we add calcium ions, and you can see that after a period of time, after incubation, after 10 minutes, the particles start to swell and uptake water, and then it plateaus off. This is a simple demonstration, and we've done a lot of work ourselves on looking at viruses, bacteriophages, and also bacterial spores, how they germinate in response to a stimulus and how they change volume, and also bacterial spores in response to disinfectants. You can follow the destruction of bacteria with time. And because the protein crystallographers use this method for looking at, I think from Dave Scott's lectures in the BIOS4005 module, you will have learned that many interesting proteins are stubborn non-crystallizers. They're very difficult to get to crystallize. You have to try out various combinations of solvent conditions to get them to crystallize. Well, DLS, non-light scattering, is a very popular way of seeing how successful these methods work, by looking for evidence of nucleation and change in size with time. So DLS instrumentation, especially the simple instrumentation, is very popular in biopharma with the big companies, and also with many SMEs, many small, medium enterprises. So that's an introduction to DLS. You should be familiar how it operates. Don't worry about all the physics behind that. That's all dealt with in the instrumentation, but at least you, by showing you this, you've got an appreciation of how the DLS operates and the limitations. It's a great technique. It's relatively low cost compared to other instrumentation. It's very rapid, but it's not as accurate as, for example, the ultracentrifuge for looking at sizes, but it is rapid, and it will allow you to follow changes in systems quite rapidly. So very popular. And again, as I said before, with modern instrumentation, the problems of dust contamination, whereas you should be as clean as you possibly can and ensuring that your samples are free of contamination. The software is very good at eliminating contributions from very large supramolecular particles. So with that, I'll finish and hand over, after a break, I'll hand over to Mary Phillips-Jones, who'll be talking about another important technique, which is circular dichroism. Okay, thank you very much indeed.